So, uh, this is question 8. Had a number of requests for this. Probably, I think, more so the second part than the first part, but I'll do it all here anyway. So a circle is shown with both an inscribed and a circumscribed square. Find the ratio of the area of the inner square to the area of the outer square. So area. You have to find the area of the inner square anyway, before you get bogged down and trying to do too much with the question. So the only thing you're told here really is, aside from the graphic, is obviously this is a square inside a circle. So that there is going to be equal to or, and that there is going to be equal to or as well. And of course, that is 90 degrees. So you can find this length here. We'll call it x. If you're going to find one length of the square, and obviously x by x is the area of the entire square. So with that in mind, we are going to use Pythagoras' theorem to find out the length of that there. Okay, off you go. Or squared plus or squared is equal to x squared. So you've got 2or squared is equal to x squared. So now that you have that worked out, the area is x by x is x squared, which is of course 2or squared. So x squared is equal to 2or squared. So that's fair enough, fairly straightforward. Now, the area of the big square is going to be that distance there plus that distance there. So you've got or plus or. This side from here to here is actually 2or. So the area of the big square is 2or multiplied by 2or, which is 4or squared. So now you're ready to look and say 2or squared to 4or squared. Well, that's the same as 2 is to 4 or 1 is to 2. That's that done. Second question, a little bit trickier. An equilateral triangle is shown with both an inscribed and a circumscribed circle. Calculate the ratio of the area of the circumcircle to the area of the incircle. So, area of circle, pi r squared. Keep that in the back of your mind. Now, depending on what you know here, you may be able to see that this is getting split up into a ratio. Okay, where that line is 3 times the length of that line there. Sorry, said that wrong. Oh, snap the shape. Hold on a second. I can just remember how to get rid of that. Need to shape off. Okay. Now, you may be able to tell from your eye that that line there should be running through the center of the circle. That line there, we have them being broken up into a ratio of where this distance is equal to this distance, which is equal to that distance. Now, you may or may not be able to work that out or know that that's the case. So you don't have that prior knowledge, it doesn't matter. What you're trying to do here is come up with some sort of ratio that will take in, that's the radius of the big circle, and that somehow takes in the radius of the small circle. So that would be capital R, that would be little r. So if you know the way these circles are constructed from your constructions, you'd know that the perpendicular bisector perpendicular bisector, sorry, this line here, sorry, these lines here are tangents to the circle. And the line from the tangent to the center of the circle does so at 90 degrees. So if you know your constructions, you'd be aware of that. So what we have here in the situation, we can draw this little construction there like that, and we can work out Pythagoras' theorem, and doing that, sorry, not Pythagoras' theorem, using trigonometry. If we have this line coming down, it's splitting it at 30 degrees. This here would be 60 degrees, 90 degrees, and using basic trigonometry, you can work out that the sine of 30 degrees is equal to opposite, which is our little r, over our hypotenuse, which is our capital R. So sine 30 is one of your special angles that you need to learn. The sine of 30 is equal to a half. So a half is equal to little r over big R, or cross multiply there, we're getting big R is equal to 2R. And if I just quickly rub that out and go back to what I was saying, you can see that what I've just said there, big R is twice the size of little r. So the big R was twice the size of your little r. Okay, so where are we going to from here? Now you have what 1R is equal to, so big R is equal to 2R. You just use your formula for the area of a circle. So the area of the big circle, pi r squared, the area of the little circle, pi r squared. I really should have used the big R there, pi r squared and pi r squared. So the big circle, pi, we know that 1R is equal to 2R, so we'll use everything in little r's here. Is equal to 2R squared, and you've got pi, sorry, r squared. So you've got 4r squared, 4 pi r squared. And here we just have pi r squared. So you can see that the ratio is 4:1. So the key to knowing this question, answering this question, was to know that the constructions, that if you created this right angle 30 degree triangle coming off the tangent, you were going to have a 90 degree angle there.